In this video, we're going to introduce and discuss the topic called the discrete-time Fourier transform. So this is different than the Fourier transform. It's the discrete-time Fourier transform. Okay, I can point you to the Orphanitis book where he talks about this way back in Chapter 1 in Section 1.5.1. I didn't explicitly bring this out at the time because I felt like we needed a little more background information before we started tackling this topic. Okay, so the idea here is we're going to take the Fourier transform, all right, but we're going to do it with a sampled data signal instead of a regular continuous time signal. So remember what we were covering way back in Chapter 1. We would have this ideal sampler, so we put an analog signal in, we multiply by an impulse train, and then what does that give us? Well, it gives us x of t is equal to x of t times delta, xs of t is x of t times delta t of t. And then when you multiply by the impulse train, the only things that matter are where the impulses occur. So all this stuff in the center is zapped out. Okay, multiply by 0 becomes 0. And you would get sum from n equal minus infinity to infinity of x of nt. These are the samples, multiplied by delta of t minus nt. So I mentioned that because, let me highlight that in red. All right, here is xs of t, and so you start with the Fourier transform definition, which is given in equation 1.5.3. And then you notice this is where, that's the signal I'm going to plug in. And so he does that in this step, plugging in the sampled signal. Okay. Then the next step is common. You interchange the order of summation and integration. So we just flip that order, do them in the reverse order. And we end up with this integral here that is actually pretty easy to work because of the sampling property of the impulse function. To do that integral, you just plug in for t at t equals nt. That's what you plug into the rest of the integrand. Okay, and what that leaves you with is our definition of essentially the discrete time Fourier transform. Okay, so I say essentially because the notation is slightly different. We're going to look later in Chapter 5 when he picks up discrete time Fourier transform again. And we rewrite this. We drop the hat business. We talk about any given sample data signal x, and we use normalized frequency in radians per second. And the definition of the discrete time Fourier transform is sum from n equal minus infinity to infinity of x of n. So we're dropping the sampling notation at all the way. E to the minus j omega n. All right, so that's what I think of when someone talks about the discrete time Fourier transform. That is the definition. Okay, so discrete time Fourier transform. Okay, I want to pause here and talk about that this is discrete time Fourier transform. There's going to also be something called the discrete Fourier transform. And yet something else called the fast Fourier transform. Okay, so the discrete time Fourier transform is defined over all omega. All right, so you notice here there's this continuous variable omega showing up. Okay, later we're going to learn that the discrete Fourier transform is different, that you actually sample in frequency the discrete time Fourier transform, which gives you something slightly different. Okay, so put that in a box for now. We'll open that up a little bit later. And then it also, the fast Fourier transform is just a fast algorithm way of implementing the discrete Fourier transform. So a fast Fourier transform is sometimes used synonymously with the discrete Fourier transform. Okay, so the key difference in the wording is this extra qualifier time. Discrete time Fourier transform is what we're going to be talking about right now. Okay, so in the Orphanitis books, he gives 6 different points that he wants to talk about in section 1.5.1. And so this video, we're just going to talk about 2 of those. Okay, and so the first one is shown here. DTFT, that's the abbreviation we use for discrete time Fourier transform. Okay, it only depends on the samples of the original analog waveform. Okay, so when we show this, okay, this depends on t equals n cap t, which is samples of the original analog waveform. That's all we need. We don't need the signal values between the sample times, and from that we can compute the discrete time Fourier transform. All right, so that's an important point because it wouldn't be useful for us otherwise. Okay. The other thing I want to talk about is when you look at this function. Okay, I'm going to go ahead and use normalized frequency. I'm going to call this e to the j omega n. All right, so we've talked about that before. So this is a normalized frequency version. This is normalized frequency version of this. Okay. What I want you to do is think about this as a function of omega. So I'll just draw a function of omega. If I take omega and I add 2 pi to it, what do I get? All right, properties of exponential show me that I get e to the j omega n, e to the j 2 pi n. Multiples of 2 pi n are 1. And so what we've established here that this particular function is periodic in omega, and the period is 2 pi. All right, so that comes strictly from the definition. Okay, and because of that, we've talked about normalized frequency and the Nyquist interval. So just as a rewind to that, all frequency on the omega axis shows up between minus pi and pi. That's a 2 pi interval. After that, everything just repeats. Okay, so he makes that point in this particular numbered section, number 2, and then he goes on to say, although it's not obvious yet, okay, the periodicity in F, I used omega, but the same thing. The periodicity in F is related to the periodic replication of the original spectrum. Okay, and so I just want to remind you of that we started with a spectrum that looked like this when we did sampling. Here's x of F. All right, and if I sample at Fs, is the sampling rate, then what I would get is replicas of the spectrum centered every Fs. Okay, and so between Fs over 2 and minus Fs over 2, I get the original spectrum. Remember, there's a scale factor of 1 over t as well. Okay, but it's periodically extended. All right, and that's really a consequence of turning things into integers instead of continuous time. All right, so just so this doesn't confuse you, you can always relabel this axis with normalized frequency. If it were omega, this would be pi and minus pi. And if it was lowercase f, remember, Orphanitis uses cycles per second for little f, I use cycles per sample. Okay, if you did that, this becomes 1/2 and minus 1/2. Okay, so that's an important start for the discrete time Fourier transform. We're going to do other videos that go through the other points in this section. This is an important section out of orphanitis.